Hello, Honors Math 3. Let's see, today is Tuesday, April 14th, and we are going to look at some algebra techniques for evaluating limits. We started limits last week. These first two examples here are just to kind of get us back in that mode from last week, some things we talked about. So if you were asked to evaluate this limit of the function sine of x over x as my x values approach 0, what would the value of that limit be? Pause and think about that for one moment. You don't have to print these notes out, but it would be nice if you had these printed out so you could have something jotted down to take away with you. Okay, if you notice, this function is undefined at x equals 0. We'll have a 0 in the denominator. That's okay. What do the function values approach, get close to, as the x values get close to x equals 0? Okay, this is a case where we need our graphing calculator because we can't get rid of that little problem spot, that undefined denominator. Remember, go to Second, Table Set, and we're going to get a table of values for that function. Oops, we have to plug that function into y1. So y1 is equal to sine of x, close your parentheses, over x. Then go to Second, Table Set. I'm going to start my table, table start, at -0.1. I mean, you have choices here. I'm just trying to get as close as possible to that x value. And I'm going to do a change of table of 0.01. After you set that up, you're going to go to Second, Table, and jot down those table values, those x and y values. Okay, when I get that table of values, I think I have to scroll a little bit in my table. But notice when x is equal to 0, I get an error that we expected. But I can also tell as my x values get closer and closer and closer to 0, you can tell what my function values are getting close to. And those function values are approaching 1. So the value of that limit is 1. As x values get close to 0, my function values are basically approaching 1. Alrighty, what about the limit of this function? What's the limit as x approaches 3 of the function 2x squared plus 1? What I notice is for x values around 3, nothing strange happens with that function. That is a slightly narrow parabola shifted up 1. So here's my parabola. Nothing strange happens at x equals 3. I can simply plug in x equals 3. 2 times 3 squared plus 1. 3 squared is 9 times 2 is 18 plus 1. And the function values are approaching 19. Nothing strange happens on that parabola. Okay? So we're going to start to talk about some properties of limits that will help us to evaluate limits. The first property we see is how to find the limit of a constant function. What do we mean by a constant function? If my function is defined as b for some number, some constant b, then the limit as x approaches some constant c of that function will be what? Oh well, let's come up with a function that's a constant. Let's say f of x is equal to 3. That's a constant function. What does that function look like? Here's a constant function. F of x equals 3 is just y equals 3. And let's say I pick any other constant. Let's say I want to find the limit of that function as x approaches, I don't know, -1. Here's x equals -1. As my x values approach -1, my function values are approaching, the function values are always 3. So if I ever take a limit of a constant function, the value will just be that function itself, that number. We have another property of limits, the limit of the identity function. What is the identity function? If my function f of x is always equal to x, is an identity function. Do you remember what that function looks like? F of x is equal to x. That's just y is equal to x, and y equals x looks like this. Given the identity function, then the limit as x approaches any old constant c of that function will equal what? Okay, here's an example of that. Let's find the limit as x values approach 10 of that constant function x. As x values approach 10 over here, as my x values approach 10, what do my function values approach? Plug in 10, I get an output of 10. That's why we call it the identity function. And my y values approach that same thing, which is 10. So for whatever constant I plug into the identity function, that limit is going to equal that value. Can you look at both of those properties and try just a couple of examples? Limit as x approaches 2, limit as x approaches -2, limit as x approaches 0. I will pause. Okay, that's a constant function 8. There's my y equals 8. As x values approach 2, my y values remain constant. As x values approach -2 on that identity function y equals x, my y values approach -2. Here's a constant function, -5, y equals -5. As my x values approach 0, my y values approach -5. Alrighty, a few more algebraic properties of limits. Let's say we have two different limits. A limit of a function f of x, for as x approaches some value, and a function g of x, as x approaches that same value c. If both of those limits exist, and we have a sum as x approaches c of f of x plus g of x, I can separate that sum into two separate limits. That's the same as the limit as x approaches c of f of x plus the limit as x approaches c of g of x. So I can evaluate those limits separately. Similarly for subtraction, if you ever have a difference of two functions inside a limit, that's the same as the limit as x approaches c of f of x minus the limit as x approaches c of g of x. I can separate across subtraction and evaluate both of those limits separately. Similarly for multiplication, as x approaches c of f of x times g of x, if I ever have a product inside a limit, that is the same as the product of two limits. I can separate those if it makes evaluating a little bit simpler of g of x. Okay, so nice algebraic properties of limits. Let's see, let's continue on. If you are signed up to take Calculus AB next year, we are going to start the year looking at limits again. Alrighty, so we will review some of the stuff we're seeing. If you are signed up to take Calculus BC next year, it's assumed that you know a lot of this, so they will move a little quicker through limits. Let's see, if you're signed up to take AP Stats next year, that's okay. This is just good information for you, especially if you take some calculus in college. Alrighty, a couple examples from those last couple of properties. Since there's addition here inside a limit, I can separate that into the limit as x approaches 3 of x plus the limit as x approaches 3 of 7. This is the identity function. If I plug in 3, I get an output of 3. This is a constant function. Output is always equal to 7. And I can evaluate those separately if I like. Alrighty, please separate this, if you would, into some products. I can separate negative 5x squared into negative 5 times x times x. This is the limit of a constant, which is negative 5. This is the identity. Input negative 2, I get an output of negative 2. Input negative 2, I get an output of negative 2, which is, what is that, 4 times negative 5, which is negative 20. What some of you are starting to say is, Mrs. Anchek, couldn't I have just plugged in negative 2 into that nice little monomial and gotten the same thing? That's a single term. Couldn't I have just plugged in negative 2? And you're right, that's a nice property of limits. We start to see that the limit as x approaches some number of a times x to the n, whatever that a value is. It's a constant, that coefficient. Really, what you want to do is just plug in that value of -2, plug in that value of -2, plug in that value of c is what you're wanting to do. So yes, we can just evaluate a times that number c to the n. That leads us to finding the limit of a polynomial. What is a polynomial? Rather than a single term, it has many terms. Here's my polynomial p of x. Let me pause just so I can jot it down for the sake of time. So here's my polynomial, which has many terms of degree n. What is the limit of a polynomial? That's the same as the limit as x approaches c of that entire polynomial. Let me jot that down again. Okay, so if I find the limit of a polynomial as x approaches c, that's the same as the limit as of that polynomial. But then if you start to notice, you could separate all of your limits across addition. You could separate all your products. You could really just plug in c like you wanted to up here. And I'm plugging c into that entire polynomial. Once I plug c into that entire polynomial, that's just plugging in c. So the limit of that polynomial, I can simply plug in that number I'm approaching. All right, so if we look at that in a few little cases here, here's a limit as x approaches -3 of just a monomial. And you're begging to just plug in -3. -3 to the third. What is that? 2 times -27, which is -54. Or calculus speaking, I like to think that's just a cubic function. As x approaches -3, nothing strange happens. I can just plug in to find that function value. This is some 4th degree polynomial function. Down, down. As x approaches 2, nothing strange happens on that function. So that means that I can just plug in 2 into that polynomial to find the function value of that, limit. -2 times 2 to the 4th plus 3 times 2 squared minus 5 times 2 plus 7. Pause and evaluate that if you would. Okay, so there's no problems on a polynomial function. I can simply plug in 2 and I got a value of that limit as -23. All right, similarly, we can find the limit of a power or a root. If I have a limit of a function as x approaches c and that limit exists, then we get these two nice properties of limits. If you ever have a power inside a limit, raising that function to a power, that is equivalent to finding the limit as x approaches c of that function and then just raising that to that power. So for example, when I have a function to a power, that is equivalent to just finding the limit as x approaches 3 of that function and then raising that to the 2/3 power. This is polynomial, it's just linear, so I can plug in 3. That's 3 times 3 is 9, minus 1 is 8. The value of this limit is 8, and I can raise that to the 2/3 power. The root is on the bottom, just like a tree. That's 8 cubed root of 8 squared, which is 2 squared, which is 4. Last property of some limits. It's also true that if we find the limit as x approaches c of a root of a function, that is the same as taking the limit as x approaches c of that function and then raising that result to the nth root, as long as that limit is defined. So then I can rewrite this as the square root of the limit as x approaches 2 of x cubed plus 1. I can evaluate this limit, which is polynomial. 2 to the 3rd is 8 plus 1 is 9. Simply becomes the square root of 9, which is 3. Thanks for tuning in today. We need to finish 14.2 on Thursday with some quotients of functions, which get a little bit trickier. Alrighty, so you have 14.2 day 1 homework today. Thanks for tuning in. Have a great day.